Hello all. So today today we will be discussing one of the problems from TIFR 2020. So this problem, it is pretty similar to the problems that we have solved in recent times, and it actually actually kind of has to do a lot with continuous functions being strictly monotone. Okay, so as you can see, the function is given. The property of the function is given to us. Let's look at it. So if I have, so this is the given function, that mod of f of x is greater than or equals to log 1 plus mod of x minus 1. All right. So the options, as you can see, are quite standard MCQ options: injective but not surjective, surjective but not injective, neither bijective. So one thing is for sure is that the first guess or the first intuition that we should have in this problem is that it is always injective. The reason behind it is, say, log of 1 plus, if you have 1 plus some positive number, then log of that number is always greater than or equals to 0, right? So if I have f of x equals to f of y, then this is 0. Hence, x has to be equals to y. So this is one way to prove it. Otherwise, rigorously, if you want to do it, you can also try this way, that x not equals to y implies f of x not equals to f of y. All right, so this is one of the equivalent definitions for injectivity. And as you can see that this is one of the equivalent definitions for injectivity. All right. So as you can see that if x is not equals to y, then mod of f of x minus f of y is strictly greater than 0. Okay. So from here it's quite straightforward that if x is not equals to y, then this term is it's quite strictly greater than 0 if x is not equals to y. Hence, we will see that f of x minus f of y is strictly greater than 0. All right. So that is why injectivity is kind of given. Not given in the question, but we can extract it quite easily from our hypothesis. So injectivity is proved. So this function is always injective. Now, one thing that you should look for here is that it is also given that your function is a continuous function. So if your function is R to R, it is continuous. It is R to, this is important. So from R to R, it is continuous and it is injective. What does that imply? So that implies that f is strictly monotone. Okay. So since f is injective plus continuous from R to R, because if I draw it, let's say if it is not strictly monotone, then the injectivity will always fail, because see, if it goes like this and comes down, then there is, so here is the violation. Here is the violation of injectivity. For 2 of x's value, you get a single y value. Okay, So that is why if it is continuous and injective, then it has to be strictly monotone. All right. So from here, in this given problem, if you look at this, so I will write it. I will write the inequality again here. So I have f of x minus f of y is greater than or equals to log 1 plus mod x minus y. All right. So now, then I can actually expand this inequality a little bit further, right? So how will I do it? So I will do it like this, that mod of f of x is greater than or equals to mod of f of x minus mod of f of y, which is greater than or equals to log of 1 plus mod of x minus y. And to remind you that this is for all x and y. As you can see that this is for all x and y. Now, so let's take y equals to 0. Since this inequality is true for all x and y in R, we can take y equals to 0. So if I take y equals to 0, what does, so let's call this as inequality 1. So what happens to inequality 1? The inequality 1 looks like this. Mod of f of x is greater than or equals to log 1 plus mod x. All right. I mean, like, I'm just punching these two inequalities in one place. All right. So from here, what you can see, you can see that if mod x tends to infinity, then mod of f of x also tends to infinity because of this inequality, because of this last inequality, right? Because if mod x tends to infinity, then this right hand side shoots to infinity. So mod of f of x is greater than or equals to infinity. That means mod of f of x is also tending to infinity. Now, why is mod x tends to infinity kind of important factor here? So since I also know that my function is both continuous and injective, this has to happen, that limit x tends to infinity, f of x is tending to infinity, and limit x tends to minus infinity, f of x is tending to minus infinity. Why so? Otherwise, the injectivity will fail. All right. So the injectivity will fail. So minus infinity. Because if x tends to infinity and both x tends to minus infinity tends to infinity, then there is no injectivity. All right. I mean, in both these parts, here and here. So the injectivity will be violated. Hence, now what do I have in my hand? So now what I have is the function, it was give f is continuous, injective, and unbounded, right? That means fx has, so practically the range of f is basically from minus infinity to infinity, and that is precisely what we wanted for surjectivity, right? Because if I want to prove some function is surjective, and where this was given like this, R to R, so then what do I want to show? I want to show that the range of f is practically R, right? So that's what I want to show. So range of f is R, and that is precisely what we have shown, because it is continuous, injective, and unbounded. As x tends to infinity, the function shoots to infinity like this, let's say, and as x tends to infinity, x tends to minus infinity, the function goes to minus infinity like this. All right. So hence there is a surjectivity as well. Thus, in this problem, you will see that this is the option that is correct. F is bijective. All right. So what did we use here? What we used here was this, that the first thing, from injectivity and continuity, we deduced that it is strictly monotone. And because it is strictly monotone now, with the help of that and the injectivity, we proved that it is unbounded and its range is from -infinity to +infinity. And because of this fact, the function f became surjective, hence bijective. Okay, so this is it for today. We will meet with another problem from TIFR 2020 next time. Thank you for attending the session.